Today we introduce another new topic, and just like with energy, momentum will be something that we derive from Newton's laws. And just like with energy, it gives us a new way of looking at some problems, solving some problems that we weren't able to do easily with Newton's laws. Although we should remember that Newton's laws were the final theory of mechanics, so we're just defining some new quantities, and those happen to be useful quantities. But it's not like we're defining some new physics. All of physics was already contained within Newton's laws. So I'll talk a little bit about the basic idea and how we use momentum. I'll define it, and also something called impulse, which you might think about as sort of the way to transfer momentum, just like work was the way of transferring energy. And then we'll derive the principle of conservation of momentum. So this is the basic principle that we'll use for solving problems, and it's similar to the principle of conservation of energy. Although I should tell you up front that the main difference between conservation of momentum and conservation of energy is that momentum is a vector. So we'll have to go back to using vector equations. And then we'll do 3 examples. So what is the basic idea? Well, first, we've talked a lot about Newton's second law. So Newton's second law, of course, is the net force, or the sum of the forces, is equal to some mass times its acceleration. So this is a law for the motion of a single particle. So we talk about, like, I don't know, an object that is sliding down a hill. We talk about the forces on that particle. So maybe there's normal, friction, and gravity. So we've talked about single particle motion quite a bit. We talk about how we find the acceleration of that single particle. But we haven't really talked much about the interaction of multiple particles with each other. And I mentioned when we first started Newton's second law that it was the complete theory of mechanics, so it includes the motion or the interaction of particles. So you could think about particles that are going to collide with each other and have some dynamics after their collision. And Newton's laws incorporate all of that. We just haven't talked about it much yet. And the way that it gets incorporated, this interaction, comes about mostly through Newton's third law. So remember what Newton's third law is. It says that if you have an object A and an object B, then when they come into that interaction there, at that moment at which they hit, then each of them will experience a force. So this is the force on B, so we write it as the force of A on B. And Newton's third law simply says that the force of A on B is the opposite of the force of B on A. So that's the fundamental principle that tells us about the interaction of 2 particles. And of course, 2 particles can go up to 3 particles when you bring another one in. We could just assume that they only hit 2 at a time, although you could put 3 together if you wanted to. And you can build your way up to a system of many particles from there. So we'll mostly talk about pairs of particles here, but there's nothing that stops us from thinking about systems of many, many particles. And so this will be sort of the beginning of our study of multiple particle systems. After we talk about momentum, we'll move on to talk about the rotation of rigid bodies, which you can think about as a collection of many particles that are sort of held together by their atomic forces. Just like we did with energy, we're going to define something that allows us to deal with the interaction of particles and to do some problems that are easier to solve than if we just use the bare Newton's second law, Newton's third law. So how does this work? Well, if we think about these 2 particles colliding, then maybe one has a speed that's greater than the other, so VB is greater than VA. At the moment that they collide, you're going to get forces, these Newton's third law pair forces, which should be equal. But those forces might not be the same over time. So this is like force of B on A, and this is the force of A on B. And so at the moment that they collide, it might look like that. And then after a moment, when they're still in contact, maybe they experience a larger force. So maybe FB on A gets bigger. And of course, because of Newton's third law, FA on B also gets bigger. And so as they come into contact, and maybe this is when they first meet, they're not even touching yet, and so there's no force, those forces can change in their magnitudes as they come into contact. So what I'm doing is I'm sort of just showing that time is increasing downward here. So although Newton's third law is a very simple rule, it says that the forces must be equal in magnitude, opposite in direction, it's not necessarily something that's easy to use, because if you're going to use Newton's second law here to try and describe how one of these particles is accelerating, then you would have to do a new free body diagram at every moment in time and use Newton's second law at every moment in time differently. So what momentum conservation will give us is it will say, okay, well, let's treat this as an initial situation. So let's put it here. So we'll say that this is the initial moment. And then we can draw a second picture, which sort of shows the collision that is happening. And then say afterwards, we have, maybe this is VA final, and maybe this is VB final. So our objects go off on their own way after the collision. And this will be the final picture. So what does this mean? We can take some initial conditions, meaning the initial velocities of the two objects and their masses, and we can relate them to some final things, which are after all of the collision happened, and we can simply relate those two quantities. We can relate, well, those four quantities. We don't have to think about what happens in the middle when the forces of interaction are involved. We can simply figure out how to relate what happened before the collision to what happened after the collision. And this is similar to what we did with energy conservation, where we took like a point A and a point B, and we related exactly what, we related what happened from point A. So maybe like you have a roller coaster that was given some initial kick here at point A. So here's our point A. So we have some roller coaster that has some initial speed here, and maybe it has some initial height above the ground. And then we might want to relate it to what's happening at this moment here, where it has some final speed at point B and some final height at point B. We were able to use energy conservation to talk about the connection between these two moments without having to think about what happened in between. That's the beauty of a conservation law, is that you say that, well, mechanical energy is conserved over all times, so I can take any moment in time, TA, and relate it to any other moment in time, TB, even though it might be 20 seconds later. As long as energy is conserved along the way, then the equation will work. So it's the same thing with conservation of momentum, and we're going to call this conservation of linear momentum, because what we're talking about is the momentum of an object's velocity as it travels through space. We'll talk about something else called rotational momentum later, or angular momentum. And so this could be used for a problem like the collision of two cars. So you have two cars that come in with some initial velocities, I'm going to call it VA, this is confusing, I'm going to call it VA and VB for the A and B cars. So this is the A car and this is the B car. And instead of using A and B for 2 moments in time, I'll call this the initial moment, then they come in and they collide, and then we can talk about the final moment. Maybe the two cars get stuck together, and then they go off at some final velocity together, something like that. And this is the final moment. So we don't have to worry about the details of the collision, but we can relate the initial conditions of the two objects to the final condition of the one object. And that's just one special case. It's important to talk about when these things can be applied. And we'll see exactly what that is for momentum, but I'll just tell you up front. We already understood this for conservation of mechanical energy. Our law of conservation of energy, not conservation of mechanical energy, but conservation of energy, was that the initial mechanical energy plus the work non-conservative, the work done by non-conservative forces, was equal to the final mechanical energy. So when are you allowed to say that mechanical energy initial is equal to mechanical energy final? Well, it's when the work non-conservative is zero, when there are no non-conservative forces doing work. So that means like when there is no friction or when there's no pushing force that's acting on them, then we can use this conservation of mechanical energy. So let's write it out. When no non-conservative forces do work. So those are the conditions that we can, when we can apply conservation of mechanical energy. So when can conservation of momentum be applied? Well, the rule here is when no forces, I guess I should say when no net force external to the system is applied. So there's a couple words in there that we need to understand. System means that we define a system of particles. So in this case, it would be like the cars, the two cars. And we restrict ourselves to only forces in between the two cars, the Newton's third law pair forces. If there are forces of other things on the cars, then we would call those a net force external to the system, meaning outside of that system that we've chosen. And if that's the case, then we can't apply conservation of momentum. So in a problem like this, we'll talk about the collision of two cars, and we'll have to say either that during the time of the collision you can ignore the force of the road on the car, or maybe the road has no friction because it's an icy road or something like that. We'll ignore the forces of the road on the car, which allows us to only talk about the forces between the cars, which is the reason that we can apply this conservation of momentum. So it's important in each of these cases to know when you're allowed to apply those laws, and in our examples we'll talk a little bit about whether each is valid and why. Okay, so now we can talk about the definition of these quantities. And we'll start with Newton's second law. And let's take the example of a pinball in a pinball machine. So this is like at an arcade. I've only drawn the pinball paddle, the thing that you hit with a little button, and a little silver pinball. So what's happening when the paddle hits the ball? Well, the paddle exerts a force on the ball, and that's going to be a normal force, and it's going to be perpendicular to the surface of contact. So there's some surface of contact there. But as the paddle turns, and I'm just using this omega here, we'll learn this in a couple of weeks, it's rotating here about its pivot point. As the paddle turns, it remains in contact with that ball for some period of time. And the normal force might be changing a little bit as it remains in contact. But what you get is you get a force applied over a time. If you remember back when we talked about energy in the past couple lectures, work was the way that we defined energy, and it was a force applied over a distance, well, there might be some work here, but what we're interested now is what is the force applied over time here? And so the reason that we're interested in that comes about through Newton's second law. So let's assume that the net force on this pinball is only the normal force due to the paddle. So I'm looking down on this system, and there might be a gravitational force into the page. There might be a normal force of the bottom of the pinball machine up out of the page, but the net force is just the force of the paddle on the pinball. So if I write down Newton's second law, then I can say, well, the net force on the pinball is equal to the mass of the pinball times its acceleration. And the net force is just this single Fn that I've drawn. And then I can write the acceleration using its definition. And its definition is the change in velocity over the change in time. I should say this is actually the average acceleration. So remember, there's a difference between instantaneous and average acceleration, but this is good enough for us to understand the basic idea. So Newton's second law looks like this in terms of velocities. And I can rewrite this equation as Fn times delta t is equal to the mass times delta v. So we can think about Newton's second law, which before was forces cause accelerations, in a different way. We can think about it as forces over time cause m times delta v's, or changes in velocity as multiplied by m. So how do we do that? Well, we define an impulse. So we define, what am I saying here? We define an impulse, and we're going to call that j, and it's going to be a vector, and it's going to be the force times time. So an impulse over a time, so maybe we should say like it's the impulse over delta t by the force. And the momentum as p, which is equal to mass times the velocity vector. And notice that both of these are vector quantities. So why did I do that? Well, this thing could be written then as delta p. So the first term is m times delta v, meaning it's m times v final minus m times v initial. But m times v final is just p final. It's the momentum final. So this is delta v. So we say that an impulse, Ft, causes a change in momentum of the particle. So this is sort of where we get the idea of momentum. It comes out of Newton's second law. It's just a different way of describing Newton's second law. And it has to do with the fact that when an object is in contact with another object, there's going to be a force, but that contact remains over a period of time, and so a force applied over time gives you an impulse, and what that means is it changes the velocity of the object. Okay? So main idea is we use Newton's second law. We didn't use some new physics, we just used Newton's second law to just define a new term, m times v, the momentum. Maybe we should put a box around that because that's the most important equation, I guess. It is the new quantity that we have, momentum. So let's look at it in a little bit more careful of an example. So if a ball comes in and hits a wall, we can imagine that that wall does not move when the ball goes there. So we can think just about the force of the wall on the ball over time. And we'd like to look at what that means for the impulse. So at this moment, there's certainly no force here because the ball has not yet hit the wall. Then we can say, well, the ball comes in and it's just made contact with the wall, and maybe at that moment, again, there's no force because it has barely touched the wall. And what I'm doing here is I'm saying as time goes by, this is what's happening to the ball. And then it makes contact with the wall, and it starts to feel a force. So there's some Fn now. And I guess here the velocity might be, well, at this moment in time, let's try and be a little more careful. So let's talk about, so at this moment Fn is equal to 0. At this moment Fn is equal to 0 still, and because Fn is still equal to 0, it still has its initial velocity right before it hits the wall. But once Fn starts being applied, then the initial velocity will be reduced because we're slowing the ball down. And then maybe the ball will sort of get deformed a little bit, and maybe at this moment velocity is equal to 0. And maybe that's also the moment at which it has sort of the largest normal force on it. Now maybe there's still a large normal force on it, and at this moment the ball is starting to turn around like this. And then as it leaves, it's going to have some, maybe we could call it the final velocity. And at this moment again, now that it's left the wall, the normal force has gone to 0 again. So we can think about the ball coming in and hitting the wall, and it starts out with some initial velocity to the left, and it ends up with some final velocity to the right. And the reason that it changes its velocity from leftward to rightward is because there was an impulse delivered by the force over this period of time. So we say that there's an impulse, J, so impulse, and I guess we should say average impulse, and that's going to be the average normal force applied over the amount of time that the ball was in contact with the wall. So that's like our delta t right there. So you could sort of average over the force value that you have during the whole period in which the ball was in contact with the wall, and you could multiply that average force vector by delta t, and that's what you get for the impulse. What should that do? Well, that thing should give you a delta p of the ball. And what is delta p? Well, delta p is equal to m delta v, which is m times v final minus m times v initial. So we can actually see what that is here from this picture, because this is just a vector addition here. It's going to be a mass, which is just a number, times the final velocity vector minus that same number times the initial velocity vector. So what is delta v vector? Well, let's do the little vector addition. The delta v vector is v final plus the minus v initial vector. And here's the v initial vector, so the minus v initial vector is this vector. And so delta v is this quantity right here. That's the delta v vector. So you can see how that works. Delta v is what you add to v initial to get v final. In other words, delta v is equal to v final minus v initial, or you could also say that v final is equal to v initial plus delta v. So delta v is what turns the velocity around from an initial leftward velocity to a rightward velocity. Maybe they have about the same magnitudes. Well, what's the dynamics? What's the reason that it turns around? This is just delta v. Well, the reason that it turns around is the impulse, and that is the average force multiplied by time. And you see it works out. So the delta v vector is going to be a rightward pointing thing, and the force, the average force, is also a rightward pointing thing. as multiplied by time. That's what relates the two things. So we're not going to talk too much more about this. The way that we're actually going to calculate things with momentum is going to be a much simpler way of thinking about things. But I just wanted you to see where this comes from. So it comes from Newton's second law. We define momentum because it sits right there within Newton's second law. And we say that forces applied over time give us changes in momentum, which just means m times delta v's. That's what it is. Now, what we'll derive is just a way of relating the p's. We'll have a way of relating the momentum before the collision to after the collision, and we don't need to think about any of these details here. But this is where it comes from. This is the reason that the things that we're going to derive are true out of Newton's laws. I should say one more thing, which is that we can write down Newton's second law. So the sum of the forces is equal to the mass times the acceleration. And we said that the acceleration is approximately delta v over delta t. And what I can do is I can bring that m inside. So I can write this as delta mv over delta t. And what is mv? Well, that's p. That's the momentum. So I can write this as delta p delta t. So this is also Newton's second law. It's just a reformulation in terms of this new quantity that we have called the momentum. And in fact, I think Newton actually wrote down his equation in this way. He talked about things in terms of momentum. I'm sure he also talked about things in terms of velocity, but if you look at the Principia, his book in which he wrote down all the laws of motion, he wrote down Newton's second law in this way. So we define momentum in terms of Newton's second law. It's this quantity p, which is m times v. And one last thing to remember, p is equal to m times v. It's a vector quantity. So we're always going to have to deal with momentum as a vector, meaning we're going to come up with some equation, the conservation of momentum, and that will be a vector equation in which we have to deal with vectors, meaning we have to do components of vectors, as we have been doing with Newton's second law. So now let's derive this principle of conservation of momentum. And I won't ask you to do this, I just want to show you where it comes from, that it comes directly out of Newton's second and third law. And in that derivation, we also see when it can be applied, when we're allowed to use it. So we're going to consider a system of particles. And for simplicity, we'll just consider that system to be just two particles. So we'll call it like MA and MB. And we're going to allow them to come in contact with each other. So when they're in contact, we know that they exert forces on each other. So we know that there will be a force on MA, which we call the force of B on A. And there will be an equal in magnitude, opposite in direction force of A on B. So this is the Newton's third law pair. These two here. Meaning we know that FB on A is equal to minus FA on B. And that's true at any moment in time. That's what Newton's third law says, is that that should always be true. Now, it's possible that these objects, these two objects, are also experiencing other forces. Like maybe there's like a normal force of a wall against MB and a gravitational force on them, and the same thing for A. Maybe there's like a pushing force over here and a gravitational force on MA. So we have Newton's third law pair forces on each object, but then each object also has some external forces, some forces that are not due to the other object. So what I'm going to do is I'm just going to combine those forces. Instead of drawing a free body diagram, I'm just going to add up the sum of each one, and I'm going to say, okay, there's also an F external on A, and there is an F external on B, whatever it is. So there's two types of forces on each of these objects. One of them is just the interaction force, the Newton's third law pair, and the other type of force is like everything else that might be exerting forces on each of the objects. So we're going to now use Newton's third law and Newton's second law to try and understand how momentum changes between these two objects, and how the total momentum of the system, meaning PA plus PB, changes over time. So we'll start with Newton's third law because it's the thing that relates the two objects. So we'll just write it down. So FB on A is equal to minus FA on B. Okay? Now, if we write down the net force for one of these objects, so let's talk about B. The net force on B can be written as that interaction force, Fa on B, plus everything else. Like that, right? So why do I do that? Well, now I can plug that expression in to my starting point up here. So I guess I need to solve for it first. So this means that Fa on B is equal to F net B minus F external B here. Okay? So I'm going to plug that in. So Fa on B then, I can plug in F net B minus F external B. These are both forces on B, as is this one up here. So I've used Newton 3 to write down my first equation, and then I've used Newton 2 to express the third law force in terms of the net force. And I can do the same thing to the other side. So this will be F net A, right? This is a force on A, minus F external A, like that. Okay. Now let's see what that gives us. Well, I could put the external forces on the same side and the net forces on the same side. So let's do that. So we get F net A, and then I have a minus F net B, so I can add it to this side. And that's equal to F external A plus F external B. Okay? I'm just going to give myself a little bit more space here. So what does that lead to? Well, I can write Newton's second law in terms of, I guess this statement here is just, so writing one of the forces on an object in terms of the net force is just really the definition of the sum of the forces. I don't know why I put a vector sign over the sum. So I'm just saying sum of the forces implies that the interaction force is equal to the net force minus everything else. So this is sum of the forces is equal to interaction plus external. At this point, I'm going to be applying Newton's second law. So now I'm going to apply Newton 2. So how do I do it? Well, I say, well, F net A is MA times AA, and F net B is MB times AB. And on the right-hand side, I can say that F external A plus F external B is just the external forces on the system of A plus B. So what I'm doing is I'm saying, okay, I'm going to consider a system of objects, which is both of these objects, and I'm going to look at all the external forces on that system, which would include the forces on A and the forces on B. The external forces on the entire system would not include the interaction forces because they are internal to the system. So they're not forces on the system, they're forces inside of the system. And we never talked about, for example, if you had a book sitting on a table, you would talk about the normal force of the table on the book and the gravitational force of Earth on the book, but you wouldn't talk about the force of one page on the next page through the glue, because that's an internal force. So external just means everything external to object A and B. So what else do we get now? Well, I can write the acceleration as I did before as delta V over delta T, and for the other acceleration, the same thing, delta V over delta T. And now I could put these things together. So what I can say is that I can bring the m inside of the delta, so this becomes delta MAVA plus delta MBVB, so the change in that quantity is equal to the total external forces on the system. But what are those things? Well, those are just what we called the momentum of each object. So this equation comes out of Newton's third and Newton's second law for the interaction of two particles. And it's at this point that we make our condition which allows us to have conservation of momentum. So we assume that F external system is equal to 0. So the sum of the forces on the system is equal to 0. And if we do that, then what do we get? We get that delta PA delta T plus delta PB delta T is equal to 0, or we could just multiply through by delta T, and we get delta PA plus delta PB is equal to 0, and I've lost my vector signs, which is bad. So what does that mean? It means that PA final minus PA initial plus PB final minus PB initial is equal to 0. And finally, we get PA initial plus PB initial is equal to PA final plus PB final, and that is our conservation of momentum law. And I should just write, to remind you, that P, this new quantity P vector, is m times v. So we need to know what that means in this equation. So it really says MA VA initial plus MB VB initial is equal to, etc., MA VA final. So we have conservation of momentum. Conservation of momentum. Another way of saying this is that P total initial of the system is equal to P total final of the system. So you take all the objects in your system, you add up their momentum vectors, that's p total initial, and that should be equal to the sum of the momentum vectors at the final time. And you notice we just used some delta t. We didn't say anything about how long that time interval is. So we're dealing with conservation of momentum between any two moments in time. And it will always be true as long as what? Well, as long as this assumption is true. So in our general equation, we used Newton's third law and Newton's second law, and that led us to this equation here. And as long as the external forces on the system is equal to 0, then conservation of momentum works out. So that's our condition. So remember, mechanical energy is conserved if there are no non-conservative forces doing work, but conservation of momentum occurs if the system has no external forces on it. And we'll see how that works in examples. Okay, here's our first example. So you're sitting in your little red wagon, and your friend throws you a medicine ball, which is heavy, 10 kilograms, and that medicine ball arrives with a horizontal velocity with a speed of 8 meters per second. You catch the ball and you throw it back to your friend with a certain speed, and the question is, what is your velocity in the wagon, both after the catch and after the throw? So let's draw this out. So here you are in your wagon. There you are. And here's your friend. And your friend is strong and is holding a medicine ball in one hand. So this is MB, and then we have MU, and we have M wagon for the wagon there. So this is the setup, but then we see what happens over time. So over time, I guess I'll try and copy this. So here you are, and initially we have the ball coming in, and we're told that it has an initial velocity of, what were we told? 8 meters per second. So it's horizontal, and its speed is 8 meters per second. I guess I should take the vector sign off. So this vector is labeled by its magnitude, which is 8 meters per second. Then in the next moment, we have you catching the ball. So now I guess your arms need to be doing something different now. So you catch the ball. And what's happening there? Well, if this came in with some initial velocity, then when it hits you, it's going to exert a force, and that will cause your velocity to change, which was initially 0. So I guess I should say VU initial was equal to 0. But in the final case, you might have some velocity. So we don't know what that is, but we'll call it VU final. And we don't know what it is. And we can imagine that it should be rightward pointing. It's probably wrong that it's going to be a longer vector than the ball, but that's okay. We'll just leave it like that. What's next? Well, what's next is that you throw the ball back to your friend. So, so now you're going to take the ball and you're going to throw it back. You're strong too. So you just lift that ball up and get it ready to go. So I guess this is still, you still have VU final, as we called it. But then in the final picture, you've thrown the ball. So now the ball is going backwards. And the ball, I guess I could call this V ball final. And we were told what that is. It's going to be going backwards at 4 meters per second. Like that. And your new velocity is not necessarily the same as your old one. So I'm just going to say VU final 2. So it's something different now. And it's again something that we don't know what it is. So I hope you can sort of see what's going on here, that we have like an initial, we could call it the initial 1 picture. So that's, when we talk about initial and final, we usually mean before and after some collision, before and after some interaction. And then this will be the final 1 picture, because in between these 2 pictures, the ball collided with you there. And then we could call these 2 pictures the initial 2 picture and the final 2 picture. So in between these 2 pictures, well, there wasn't a collision, but there was sort of the opposite of a collision. You had the you with the ball, and then finally you without the ball. So that's, I don't know what you call that, anti-collision? I'm not sure. But in between, there's something that happens. That's what we mean by initial and final pictures. And what we can do is we can apply conservation of momentum here, and we can apply conservation of momentum here. So we should be able to relate the initial velocities of the objects in this picture to the final velocities of the objects here, and the initial velocities of the objects in this picture to the final velocities here. So we have sort of 2 objects, the ball and you in the wagon. So let's do it. So our basic principle is conservation of momentum. And let's put a question mark after it, because remember, we can only use it during certain cases. So the idea is we're allowed to use conservation of momentum when there are no external forces on the system. So what is our system? Well, if we look at our initial picture, it's going to be the ball and you plus the wagon. So that's our system. So it's the ball and you wagon. Okay? Are there external forces on the system? So we need to ask that question before we can even write down conservation of momentum, because conservation of momentum is not true unless that's true. Well, I guess there are no external forces. So in an approximation, I mean, there's probably air resistance on the ball, there's probably some friction on the wheels, there might be some friction with the ground, but basically there are hardly any external forces. So we're going to assume that the normal force and gravity are balanced here, so they don't contribute to a net external force. And instead, the only forces are the forces in between you and the wagon and the ball. So what that requires is that these velocities are all horizontal. If you threw the ball upward, then there would be an extra normal force because of the ground on you, and that would negate this external forces going to 0. So we're going to assume that that's not true. F external is equal to 0. So yes, momentum is conserved. So we can use our conservation of momentum. So let's do it in the first case. So in step 1, we have, we could say P total initial is equal to P total final. That's sort of our basic statement of momentum conservation. And by P total, we mean the sum of the 2 objects. So P ball initial plus p u wagon initial, and that should be equal to the final. So p ball final plus p u wagon final. Okay. What are those things? Well, momentum is m times v. So this is the mass of the ball times the initial velocity of the ball. Notice that I'm drawing vectors over everything. And then it's the mass of u and the wagon together times the velocity of u and the wagon. And then the same thing for final. So m ball v final, v ball final, plus m u wagon, v u wagon final. We're just going to start to get lots of subscripts here. Okay, so this is just the equation. So as you know, we always want to start out with our basic law to say what we're doing, then you plug in what these things mean, and you get to a basic equation before you've really even done anything. But now we can use our pictures to figure out what these things are. And just like with Newton's second law, what we do with a vector equation is we first look at coordinates. We choose coordinate directions. So I'm going to choose a coordinate system, and here I'm going to choose an x-axis that points in that direction. And then we express components in terms of magnitudes of vectors. So let me just give myself a little bit of space here. So we have a vector equation here, and that vector equation should also be true for the x components. So I can rewrite it. mb vix plus mu wagon vu wagon initial x. I guess this was v ball initial. And then we have mb v ball final x and mu wagon vu wagon final x. I told you there's going to be a lot of subscripts. But you know what this means. You have a vector equation, you look at it in terms of components. And now we just go through and find each component from the picture, meaning comparing the velocity vector to our x direction. So what do we get? Well, m ball, v ball initial x, that's this vector on this coordinate system. Well, it's positive. So I write it as m ball times v ball initial, the magnitude of the ball. Then mu wagon times vu wagon initial x. Well, what is the initial velocity of u? It's 0. Both u and the wagon are sitting there at 0. So that one goes to 0. Then m ball v ball final x. Well, I guess that's just the final velocity of u and the ball. So I could actually just call this v final here, because both you and the ball and the wagon, you all have exactly the same final velocity. So this is going to be m ball times v final, and I'm calling it positive magnitude because this vector points in the positive x direction. And then we have mu wagon, and then vu wagon final. Well, that's also v final, like that. So what do we get? Well, we can write this as, I can combine these two terms, and then I can divide by them. So this is v final times m ball plus mu wagon. So that means that I can write v final is equal to m ball v ball initial over m ball plus mu wagon. So I can find the final speed of u. And let's just plug it in and find the answer. So we have, so m ball was 10 kilograms. So we have 10 kilograms times the initial speed of the ball, which was 8 meters per second. And then we divide by the total speed of the ball and you and the wagon. So that's 10 plus 60 plus 20. So 10 plus 60 plus 20. And that comes out to be 0.89 meters per second. So certainly I shouldn't have drawn this vector so big. Sorry, I guess I'm talking about this vector here as compared to this one, because this is 8 and this is about 1 here. So the speed is much smaller, but there is some speed and it's rightward. So we found it. Okay, that was the answer to the first question. What is your velocity after the catch? And then you're going to throw it, so what's your velocity after the throw? Well, we have exactly the same setup. We still have the two objects here. I'm just going to skip ahead to this equation here. So I can copy it actually. Because I have exactly the same setup, I have two objects. I have an initial and a final, and I have everything along the x direction, which I'll choose to be exactly the same. So I choose a coordinate system again, and I'm going to use that x direction. Now, what is my initial and my finals in this case? Well, my initial of the ball is going to be what I was calling v final here. A little confusing, but that's what's going on. So we have v final there. So that's going to be, that's a rightward pointing vector. And so v final for both you and the wagon and the ball, you're all going to the right with v final. That's this number here. So I'm just going to write that. So it's mb times v final. And then we have mu wagon also times v final. So you see what I'm doing here. I'm saying the x component of each of these objects initially in this picture is pointing to the right, and it has a v final there. Then we look at the final of the second case, and we have to look at what's happening here. This one gets a little bit tricky. So now we have m ball, and we have the final velocity of the ball, meaning here. Well, that's a vector that points to the left, and that means that it has a negative x component. So this is going to be minus v ball final. So v ball final is a different vector than v final was. And then we have mu, and you have a new vector as well, which we called vu final 2. So we'll write that. So this is going to be vu final 2 there. Okay, so it's a little bit confusing because I said my initials are my finals, but that's because I'm using, for the initial case of the second problem, the final velocity of the first problem. But I hope you can see that. And now I can solve. So the question is, what is VU final? And so I can solve for that. So we have MU wagon times VU final 2 is equal to M ball plus MU wagon V final plus M ball V ball final there. And then I can divide that whole thing by MU wagon to get VU final 2. So now we just plug all of that in. So we have M ball, which is 10, plus U in the wagon, which is 20 plus 60, so that's 80. We multiply that by the final velocity that we got from the first case, which was 0.89. And then we add to it M ball, which is 10, times the ball final speed, the one that we were given as 4 meters per second. So that's 4. And then we divide the whole thing by the mass of U in the wagon, which is 60 plus 20, that's 80. And so we get V final is equal to 1.5 meters per second. So what did we find? We found that if your friend throws you a ball here, and you catch that ball, then you'll start to move with the ball. You're not going to move with the same speed that the ball had because you have mass. So conservation of momentum says that mv of the ball will become total m times v of u here. So the sum of the ball plus the wagon plus u times the velocity will be the same as what we had in the initial. That's what we did in this case here. So we found that it was going to be a smaller speed after you catch the ball than the ball had originally. But then if you take the ball and you throw it backwards towards your friend, then you'll again gain velocity because here you had one object moving to the right, and here you have an object moving to the left and an object moving to the right. If the sum of these two vectors here is going to be the same as this vector here, then it must be that the rightward pointing one is bigger than it was here. Okay? I'll say that one more time. The idea is, maybe I'll draw it in red. So there's some p initial vector here. There's a p initial vector for the second case. And we know what conservation of momentum tells us is that the p final vector must be exactly the same. The p final vector is the p initial vector. Well, how do you get the sum of these two vectors to be the same as this vector up here? Well, it must be that this thing is going to be longer. It has to be longer because you take this vector, the mass times the velocity, and you add a leftward pointing thing to it, which will bring you back, and that leads to the same thing. So conservation of momentum means that you're going to go even faster after you throw that ball backwards. In fact, this is how rockets work. So when a rocket takes off, it's not like the rocket is swimming with the air like a plane with a propeller does. A propeller basically just pushes on the air. No, what a rocket does is it throws pieces of itself backwards, and that makes the rocket go forwards. So rocket fuel is just something that explodes and is thrown out the back of the rocket that allows the rocket to go forwards. Okay, that's our first example. Let's try another one. So you're going to go curling. This is that winter sport where you slide rocks across the ice and try and get them into the bullseye. But your friend has a normal curling stone, and you only have a kid's one, so it's a smaller mass. Your friend slides their stone at yours, which is sitting at rest, and after it collides, the stone is moving in a certain direction. So we can see that this is a case of an initial situation and a final situation. So let's draw a picture for those two. So we have your friend's stone, which we're going to call MA here, and we're told that it moves with an initial velocity of 4 meters per second. So I'm going to call this VA. Let's just be simple about it. We won't worry about the initial. And it's headed towards your stone, which is MB, and MB is smaller, so this is 11 kilograms, and this is 18 kilograms. And the initial velocity of your stone, so VB, is equal to 0 here. That's the initial case, so we could label it initial case. And then in the final case, well, here's where that stone was. It came in, it hit your stone, and then we're told that your friend's stone goes off at an angle of 30 degrees with respect to the original path. So this was the original path, and your friend's stone is going to go off like this. So this angle is 30 degrees, and here it is. So this is MA, and it has a final velocity that points along its path. So this is called VA final, and we're told what that is. Oh no, I'm sorry, I screwed it up. So they collide, and then your stone goes off at 30 degrees. Well, we can have it go the same way. So your stone goes off at 30 degrees, and here it is. So this is MB, and it has a velocity along its path of VB final, and we know what its magnitude is. It has a speed of 3 meters per second. And this angle, as we were told, was theta is equal to 30 degrees. So this was the collision here, happened at some moment in time before this picture. This is our final picture. And we want to know exactly where does the other stone go. The question is, what is the velocity of your friend's stone after the collision? Well, remember, momentum initial is equal to momentum final. Now that's going to be allowed as long as there are no external forces in the system, and we'll verify that in a second. So what it means is that the initial momentum vector, which is just ma times va, so that's a rightward pointing initial momentum vector, must be equal to the sum of the momentum's final. Well, this one points up and to the right. And if you're going to get an up and to the right vector added to something else that must point directly rightward, because the final has to be exactly the same as the initial, then it must be that your friend's stone has to go sort of here. I shouldn't have drawn it so symmetrically. Maybe we'll draw it like this, where there's some other angle that we don't know, and your friend's stone, MA, is going off at some other direction with some other speed, MA final, like that. So somehow the sum of this vector, m times the velocity, plus this vector will give you a rightward pointing vector, as we need, because that's what our initial momentum was. So that's how we analyze these pictures. So is it true that we're allowed to use momentum conservation? Question mark. We'll say yes, because on ice, meaning the force of friction is equal to 0, and there are no other forces on the system. So I'm looking downward at this ice rink. These stones are sliding on the ice, and there's basically no friction on them. There is a normal force and a gravitational force. Those would be perpendicular to this page, but they balance out, so there's no net external force. So let's just state that explicitly. So F net external for the system of the two masses is equal to 0, so momentum is conserved. Well, that's good, because that's what we wanted to use. Okay, so let's write it down. So P initial is equal to P final. So P initial is equal to P final. And that's going to be PA initial plus PB initial is equal to PA final plus PB final. That's equal to MA VA initial plus MB VB initial is MA VA final plus MB VB final. This is our vector equation. You could think of this as sort of like our Newton's second law vector equation. And what do we do with it? Well, it's a vector equation, so we choose coordinates, x and y, and we write down the x equation, and then we write down the y equation. In the previous case, we only had to write down the x because everything was along a line, but here we obviously have vectors in the y direction as well, so we'll need to include both. So the vector equation must also be true for the x components. So I write it out. MA VAIX plus MB VBIX is MA VAFX plus MB VBFX. Okay? Now we look at our picture. So what do we have? Well, in the initial case, the rock B was not moving, so that thing's going to go to 0. In the initial case, the velocity of the A stone is moving to the right, so on my x-axis, that's a positive VA. So I can write this component as just VA magnitude. So I hope you see this and you recognize this is the same thing we were doing for vector equations with relative velocity and with Newton's second law. We start out with the vector equation, MAVA vector. We look at its component, MAVAX, and then we express the component in terms of the magnitude of the vector meaning I say, okay, this vector here has a positive x component, so I write it just as ma times the magnitude of the vector. Do the same thing on the other side. What is mavafx? Well, this vector here, I don't know what it is, but I know that it should point generally in this direction, and it's going to have a positive x component. So I'm going to write that as, well, so there's two ways that I could do it. I could write it as ma VAF magnitude times cosine of phi. That's one alternative. I think what I'm going to do instead is I'm just going to leave it as an x component, and then I can just solve for the x component itself. So that's an unknown x component. The reason that I might do that is because that way, if I did it the other way, I'll have the angle in both of my x and y equations, and I'll have to somehow combine them in order to solve for that angle. I think this might be easier. What is MBVBFX? Well, this one I don't need to leave because I can see exactly what it's going to be. It's going to be MB times VBF magnitude times cosine of theta, where theta is a number that I know. It's this 30 degrees here. So this equation is an equation for VAFX. VAFX is equal to MAVA minus MBVBF cosine of theta divided by MA. Just doing some algebra on that. We can actually solve that for a number now. So what are they? Well, MA was 18 kilograms, MB was 11, so we have 18 times the initial speed was 4 meters per second, so 18 times 4 minus 11 times, and the final speed was also given to us for yours, it's 3. So 11 times 3 times cosine of 30 degrees. And then we divide that whole thing by the mass of your curling stone, which was 11, and we get 3.94 meters per second. Okay? So that is the x component of the final velocity of this stone here. How do we get the y component? Well, we need to do our vector equation, so we need to find the y equation. So we just rewrite the vector equation in terms of the y equation. So we have y is ma va initial y plus mb vb initial y is equal to ma va final y plus mb vb final y. Okay, that's what comes out of this vector equation, but for the y direction. Now we go back to our picture and see what they are. Well, in the initial case, VB is equal to 0, so it's going to have a 0 y component. But VA is horizontal, so it points along the x-axis, and it also has a 0 y component. So we write this as 0, and this is 0. Very simple left-hand side. On the right-hand side, well, as we said last time, I'm not going to try and find the angle of it right now. I'm just going to call it some y component. It should be negative, but I just write it out. So VA final y, like that. Then we have MBVB final y. Well, that thing has a positive y component, and it's going to be equal to the magnitude times sine of the angle. So it's going to be MBVB final sine theta. And this is an equation for VA final y. So VA final y then is equal to minus MB VB final sine of theta all over MA. And it makes sense that it's a negative number, right? This is minus times a bunch of positive numbers. It makes sense that it's negative because we saw that it should be pointing down if this one is pointing up in order to get a horizontal total momentum vector. So what is that? Let's just plug it in. So MB is yours, that's 11 kilograms, times VB final, which we said was 3 meters per second, times sine of the angle, and then divided by MA, which was 20, right? No, 18. So this becomes minus 0.92 meters per second. So the question was, what is your friend's stone's velocity after the collision? And it's going to be equal to VAFX, comma VAFY, which is plus 3.94 meters per second minus 0.92 meters per second. And that's the final moment, that's the final velocity. That was the first question. The second question is, was mechanical energy conserved? So mechanical energy is equal to kinetic plus potential, but in this case it's just equal to kinetic because flat ice and no springs. So in this case, conservation of mechanical energy just means kinetic energy initial equals to kinetic energy final. So let's see if this is true. So kinetic energy initial would be 1/2 ma va squared, because we only had one thing moving in the beginning. And then kinetic final would be 1/2 ma va final squared plus 1/2 mb vb final squared. And we need to see if that's true. So let's look. So we have 1/2 ma va squared. So what is that going to be? Well, it's going to be 1/2 times 18 times va initial was 4 meters per second. So that thing is 144 joules. And in the final case, well, I need to find the magnitude here. So the magnitude is the square root of these things squared. So VA final is going to be equal to the square root of 3.94 squared plus 0.92 squared. And that is 4.0. Oh dear, this is bad news. So that thing is also 144. And we can see that it's not going to be conserved. In fact, we're going to get more energy in the final case. That's why I said, oh dear, bad news. So MB is 11, and MB final was 3, I think. And so this came out to be about 50 joules. And so our final was larger than our initial. So this is possible, but it's a very special case that can do this. So our energy increased as they went through. So I should come clean. The reason that our energy increased is because I set up the problem poorly. I must have done something wrong when I was checking whether it would work or not. Without any energy being input to the system, you can't get a 3 meters per second for the final one. So what, if this actually did happen, then what must have happened is that there was some sort of explosive device on your own curling stone that allowed it to go off with this velocity. Momentum is still conserved because that explosion between the two is an internal force. So it doesn't count as an external force on the system. So everything we did with momentum conservation is true, but in order to get a final energy which is larger than an initial energy, there must have been some energy input here. So I should have set up the problem so that this was smaller, and that would allow for an energy that would be allowable with energy conservation, although the two are completely disconnected. And what you would normally see in something where there is not an energy input is that you lose some energy due to the collision, and therefore energy is not generally conserved here when momentum is conserved. So let's write that out. So must have been an explosion to get kinetic final greater than kinetic initial. Usually energy is lost in a collision. So the basic principle is conservation of momentum does not imply conservation of energy, which we see here. We found exact conservation of momentum, we assumed it, and we did not find conservation of energy. The energy did not remain constant. It actually increased, unfortunately, which meant that there must have been something going on when those two things collided. Okay, we'll do one more example. Figure skaters, Mark and Francesca, are standing face to face with their palms touching. They push off and glide backwards away from each other. First question is mechanical energy conserved? And second question is, if Mark travels at 3 meters per second, how fast does Francesca go? So let's just draw these figure skaters as boxes. So we have Mark and Francesca. They're initially touching each other, and their initial velocity is equal to 0. So let's actually say V Mark initial is V Francesca initial is equal to 0. So that's our initial situation. Remember that the general method here is we draw a picture for the initial situation, and then we draw a picture for the final situation. So in the final situation, they're separated, they push off each other, and they get velocities. So V Mark final, we're told, is equal to 3 meters per second, and V Francesca final is unknown. We don't know what that is. So what do? We do conservation of momentum. Our first question was, is mechanical energy conserved? So this is the same situation as curling. We're looking down on them, and they're on ice. And so we're wondering whether mechanical energy is conserved. They're on this flat ice, so there's no potential energy due to gravity. So mechanical energy initial question mark equal to mechanical energy final just comes down to kinetic initial equal to kinetic final. Well, kinetic initial was 0, and kinetic final is 1/2 m Mark V Mark final squared plus 1/2 m Francesca V Francesca final squared. Well, we know the answer already. No. Energy is not conserved. So this is exactly like what just happened with the curling ball, the curling stones, except in this case we can sort of understand why. So mechanical energy is conserved when, do you remember? No non-conservative forces do work. So we'd get conservation of mechanical energy as long as there are no non-conservative forces doing work. Well, here they are pressing their palms against each other, and that normal force on each other is a non-conservative force, and it's doing work. They're both doing work on each other, and that inputs energy to the system. So there is a little explosion that is happening as they push off of each other, and that explosion is adding mechanical energy. You could think about how do we get total energy conservation? Well, those two people are putting some energy into it. They ate some food in the morning. That gave their body some energy that allowed their muscles to do work, and that energy was input. So here we have kinetic final greater than kinetic initial, just like we had in the previous one, although I didn't mean that to happen in the previous one. So what about part B? So part B says, if Mark is traveling at 3 meters per second, how fast is Francesca going? So we need to figure that out. So the initial momentum should be equal to the final, as long as there are no external forces on the system. So again, on ice, there's no friction, there's no gravity, the ice is not at an angle, so that means there's no external forces. And now we need to write it out. So we have m Mark, v Mark initial, plus m Francesca, v Francesca initial. That's the sum of the initial momentums. I guess they're called momenta, plural. Then we have m Mark, v Mark final vector, plus m Francesca, v Francesca final vector. It's a vector equation. We have to deal with it as a vector equation, but in this case it's again simple that there's only things along one line, so we only have to look at the x components. So we rewrite this equation as an x component equation. M Mark, v Mark initial x, m Francesca, v Francesca initial x, m Mark, v Mark final x, m Francesca, v Francesca final x. And then we go through and we find each component. Well, in the initial case, we know that they were motionless, so both of these are 0. Right? In the final case, well, let's go back and look at Mark's velocity vector. Mark's velocity vector points backwards in the negative x direction. So we're going to write that component. We have m Mark times minus v Mark final magnitude, because its x component is negative. Francesca points in the rightward direction, so we have m Francesca times plus v Francesca final. That's our unknown variable, so we can solve for it. So v Francesca final is equal to, well, it's going to be m Mark times v Mark final, adding it to the other side, and then dividing by m Francesca. So what is that? Well, we're told that m Mark is 3 meters per second, and their masses are 80 and 50. So we get 80 times 3 divided by 50. And we see that Francesca moves faster than Mark. She moves at 4.8 meters per second. So conservation of momentum, conservation of P, which is m times v, means that because Mark has more mass, Francesca will be going faster in order to get their MVs equal. And the reason their MVs are equal in magnitude is because the initial momentum was 0, so the final momentum must add up to 0. Okay, I'll see you next time where we'll talk a little bit more about momentum in terms of collisions.